Okay guys, in this video segment we're going to talk about significant figures and how they pertain to recording properly precise numbers coming from measurements. Okay. Now, when we start talking about this word significant, a lot of times people say that the word significant to them means important, which I would agree. However, there are a lot of things in this world that are important that really aren't significant. In class, I talk about the idea of apologies. So if you have an apology and you're being made to apologize like a little kid, there really isn't any significance behind that apology because you're being forced to do it. However, if you apologize to a friend or a colleague or a little brother or sister or anybody and nobody's making you do it, and you do it because you truly are sorry, that's significant. And now no one's forcing you to do it, but you do it because you want to. So I sometimes challenge my students to think of significant meaning things that are done that don't need to be done. Okay? Because significant things in your life are things that happen that don't need to happen. All right? So the word significant really isn't about is it important or not, because all numbers we write are important. It's more about when do we writing numbers that have meaning to them. Okay? Now, in the world of science, numbers with meaning come from measurements. So if I had my choice, we'd actually take this idea of significant figures, I would cross out the word significant altogether, and I would change that word with measured. Okay? So significant figures really are just measured values in some sort of scientific application. The reason why we had to talk about this is because once you measure a number, there's some sort of error involved there. Now, when you're measuring with significant figures, you have to keep in mind that all measurements have error. And when you're using a different measuring tool, you want to make sure that you always measure to the precision of the instrument plus whatever that possible estimate is that you have. Okay? So for example, if we do something on the board, if I have a measuring tool that puts a line in, and then say this is 1, 2, 3, 4, 5, etc. Whatever this measurement is, maybe it's a decameter or something to that point. Okay? And if I have something I'm trying to measure, and I say, okay, how long is some sort of object I have? So this would be maybe my 0 point out here. Okay? So let's say I have something, I don't know, we'll just grab this thing right here. Say, how long is this? So I put it up here, I measure it, and it goes to there. So is it 3? Well, no, it's less than 3. Is it 2? Well, no, it's more than 2. So a good measurement would estimate in between those two numbers. So the tool that we're using tells us it's 2 something, and then the estimate comes from the person doing the measuring. And since I think it is almost all the way over, I'm going to say it's about 2.8. So this is the limits of the tool. This is my estimate. Okay? Whenever you are measuring, you need to put in your estimate. What it does is it actually increases the precision and actually makes the numbers better. Because it's not 3, it's not 2, it's closer to 2.8. Now, 2.8 might not be perfect. It might not be exactly right, but it's better than saying 3 or just 2. In fact, when you say a number like 2.8, I like to tell my students that what you're really telling the world is that it's somewhere close to that. So maybe it's as low as 2.6. Maybe it's as high as 3. Now that's a pretty big range for this. We know it's not as high as 3. You can probably be pretty confident it's not as low as that. So you might say, well, that's kind of silly. But 2.7 to 2.9, that might be realistic in terms of what does this number mean to us. So 1 up, 1 down. If someone says, no, I think it's 2.7, it wouldn't be a huge difference. It would be it'd be within the estimate that you had also. Okay? So whenever you work with measurements, you have to measure to the precision of the instrument plus whatever estimate you have. Now that estimate then tells us things like this, that my number is somewhere close or somewhere in this range. But working with ranges is hard in terms of math, because if I ask you to multiply this, how do you multiply a range? Okay, you can, but it's not within the scope of this class. So instead of doing this, we just estimate to a single value, and that's our best estimate. Okay? So within this system, we're going to say no more asking how do I round things. Because when we're done talking about significant figures, we're going to lay it out in terms of how everything gets rounded. Okay? All our measurements are based off the precision of the instrument. And then what's nice about significant figures is when you're measuring your own tools, using your own tools to measure, you know your significant figures because you know the precision of the instrument you're working with. However, the hard part about sig figs is when you're working with somebody else's numbers. So you're reading it out of a book or a table or a graphical or pulling out standard data, or maybe you're just reading somebody else's work, a peer's work. You need to know the system within how we work with numbers to know what is measured, what is not. So that's the first part we're going to start with here, is how do you identify what is measured, what is not measured, okay? Once we can do that, then we can use this information to help us do the math that goes along with measured numbers. So we have basically 4 rules I talk about in terms with figuring out what is measured, what is not. Now again, we're called this counting sig figs, but really you could say the same thing as identifying measured values or counting measured numbers, because that's what we're really doing here. So rule number 1, easiest rule we have, anything that's not a 0 is significant. So 1 through 9, if you see it as part of a measurement, it has to be one of our significant or one of our measured values. Rules 2 and 3 tell us how to deal with zeros, because sometimes zeros are placeholders. They're still important, they're still required for the math reasons, but they're not measured. And sometimes zeros are actually part of a measurement. So because a 0 can be one of the two, we have to have a rule to determine which one it is. And then finally, if you have a number that's not part of a measurement, we always say it has an infinite number of sig figs. Okay? Because we don't want a number that's not measured to limit our precision. Whereas anything that's not measured really is an exact number. For example, counting. So if you want to say there's 25 people in a room, you can count 25 people. You didn't really measure that. So there is no possibility that there's 25.2 or 25.4 people there. It's either there's 25 people or there isn't 25 people. Okay? So that isn't a measured number, that's a counted value. So counted values, like other things that don't have units on them, are infinite. So they won't minimize our precision. Now let's take a look at some numbers and work through these different rules. So on the screen what we see here is our first number is 5,500 grams. Okay? And then we have 0.0055 grams. So let's start with those two. So 5,500 grams. We want to figure out what in this number is part of the measurement, what is just placeholders. So our first rule tells us that anything that's not a 0, the 2 5s, are part of the measurement, or they are significant. Now, rules 2 and 3 tell us about these zeros. And we have to start by asking ourselves the question, do we see a decimal or not? So if we look, there is no decimal here, there's no decimal anywhere else, so there is no decimal, which means we need to apply rule number 3. Rule 3 tells us we start on the right-hand side of our number, we work our way to our first non-zero, that value and everything else to the left is significant. So I start over here, and I'm going to work my way this way. I skip this 0, I skip this 0, I find my first non-zero, which is a 5. It's also, we already know it's measured. That's where the measurement begins. So this number and then anything else over here is part of the measurement. So these two zeros are just placeholders. Okay? They're not part of the measurement. Now, are they important for me to write down? Oh yeah, they're important. Because what happens if I get rid of them? I go from 5,500 to 55. And I can't do that. Okay? So we need to have them here to hold the place of the 5s, but they're not part of the measurement. So they're not part of our significant figures. Now what this tells us is that this number has 2 layers of precision to it, which later on was going to tell us how many layers of precision numbers that we calculate off this can be determined. Okay? So that's our first example. Now if we go on to the next example, we had 0.0055 grams. In this case, again, we know the 5s are significant. We do see a decimal now, so here's a decimal that we have to work with. And because we see a decimal, we'll apply rule number 2. You see a decimal, start on the left, go to the right. So I'm going to start on this side now. And I'm going to walk this way. Again, skipping that 0, skip that 0, skip that 0. These are all zeros before the first non-zero. As soon as I hit my first non-zero, that starts my measurement. And then anything else to that side of it is also measured. So again, the 2 5s are part of the measurement, but these zeros are just placeholders. Okay? They're required mathematically, but they're not part of the measurement. So this number also would have 2 layers of precision. Now the easy way that we say that is that both of these numbers have 2 sig figs. Stands for 2 significant figures or 2 layers of precision within that numbers. They both have that for these 2 examples. Okay, let's go around and do a few more examples. I'm going to skip down on our list on the screen, and I'm going to go down to number 5. 5 is 50500 grams. Oh, one more 0. Okay. Applying our rules, we do not see a decimal, so I start on the right. I work my way here until my first non-zero. That's where the measurement starts. And then everything over here is also measured. So this 0 is and this 5 is. So now I have 3 sig figs. Okay, I'm going to jump down to number 6 now. Number 6, 0.0050550. In this example, I see a decimal, so I start on the left, I work my way to the first non-zero. That's where the measurement starts. And then everything to the right of it is significant. So this one is, and this one is also. So this number would have 3 sig figs also. Okay? Okay, I'm going to end this video segment here because that gives us the basics behind how do you count significant figures. Feel free to do additional practice with this. And in our next segment, I'm going to talk about the special cases and some of the other numbers on our list here from 7 down to 13 and why maybe those are not measured values and help you out with that. Okay, thank you.